Today we are going to talk about some very hot topics such as how to speed up GC applications, maximize gas usage, and how to convert methods from traditional carrier gases such as helium to gases like hydrogen. But first, there are a few misconceptions that are made about GC methods that I would like to address. Here are some of the comments I have heard from people when the topic of speeding up, optimizing, or changing a carrier gas for a method have been discussed and how I'm probably going to reply 99% of the time. Number 1, GC methods are supposed to be long. Other than long being a very objective term, this is a very false statement. A lot of older methods or methods that haven't been properly optimized due to using traditionally longer columns, wider diameters, improper phases, or phase ratios may use a longer GC runtime as a crutch to get more resolution between compounds. There have been a number of improvements in GC columns as well as flow technology that can be used to decrease the overall time of your GC method. And there are also some methods where you could drive a truck between two peaks and still have room on both sides, which end up causing a very long GC runtime, and that's unnecessary. As long as you can still maintain resolution of your compounds and identify them properly, there's no reason to need to have 5 to 10 to 20 minutes between your peaks. Number 2, the myth that you have to hold your runtime at a high temperature to get all of the junk off your column. First of all, we need to examine why this junk is there in the first place. Are we doing an adequate job of preparing our samples to get rid of unwanted matrix? Also, backflush is a great tool that can be used to stop that junk midway and push it out through your split vent trap so you can stop your run at a much lower temperature. Number 3, the idea that it is normal to bake out a GC column after every injection. No, please don't do this. Frequent bakeouts of your GC column will decrease the overall lifetime of your column and will also lead to more downtime of your GC when you are having to replace these columns. There are also 2 maximum temperatures on each GC column, often seen as MAOT, or the maximum allowable operating temperature. The lower of the 2 temperatures is the isothermal max temperature, and this is the temperature the column can hang out for longer periods of time. And the higher of the 2 temperatures is the program max temperature. This is the temperature where the column should only be for short periods of time, say around 10 minutes. What is important is to never exceed these 2 temperatures. That is when you start to kill your column. Number 4, and this one's my favorite. This method has been around since the 1980s and was created by a super chemist named Bob. And Bob knew everything there was to know about chromatography. So why am I going to try and recreate what Bob did? Now, while I'm sure that Bob knew a lot when it came to chromatography in the 80s, because Bob probably was on the front line of the advancements of chromatography, from packed columns to blowing your own glass columns to early polyamide-coated fused silica columns, Bob learned a lot. But there have been so many innovations since then. Back in the 80s, people were using floppy disks, needing a rolling suitcase to take a portable computer home, and listening to 8 tracks. Today, we have gigabit USB drives, computers that fit into the palm of our hand. And not only can we stream music, we can listen to it on tiny AirPods or earbuds. What I mean to say is that since then, we've been open to so many other innovations that we use in our daily lives, and it would be silly not to welcome them into the world of chromatography. There's a lot of ways that you can speed up your analysis, and there's no one right way. Let's talk about all the things that we can do to speed up our GC method. Your carrier gas selection will have an effect on your linear velocity and how fast your analysis will go. I'm not going to go into too much detail on this at the moment, but just by switching from helium to hydrogen, you can increase your linear velocity and maintain proper peak shape without making changes to your gas flow. Other things that can be done are changing the stationary phase of your column you are using to something that will have less retention. Making changes to the oven temperature program, whether that be starting at a higher temperature or increasing the ramp rate of the oven program, can also help. And if the type of column phase is correct for your compounds, you can also decrease the column length, film thickness, and internal diameter of the column to speed up your method. And if the only reason you are having a very long runtime is to get rid of unwanted gunk off your column, you may want to consider using backflush. Increasing your oven ramp rate will speed up your overall method, But this is something I like to say to proceed with caution on. Don't just jump from a 10-degree a minute ramp rate to 200 degrees per minute ramp. Here's why. When changing a temperature program, like increasing a ramp rate of an oven, yes, you will have to worry about decreasing the resolution between compounds, but you may also have to worry about changes in selectivity. Gases have different viscosities at different temperatures, so when you either increase your ramp rate or increase your initial starting temperature, your compounds may elute at a different temperature, and the difference in gas viscosity can change the thermodynamics and affect your selectivity. This is especially apparent in methods that use constant pressure mode. I'm not saying that your latest eluting compounds may suddenly jump to the front of your run, but I am saying that if you have a lot of analytes of interest, like say analyzing pesticides, then you should proceed with caution and verify the locations of all your peaks and maintain your resolution is acceptable for your analysis. Let's talk about some other things besides changing carrier gas that will help speed up our method. One concept that we learn when studying chromatography is that if we want to increase our resolution between peaks, the easiest thing to do is increase the length of your column. This will not only increase your resolution, but will also increase your attention time and your runtime. But since you don't get double the resolving power from a column twice as long, column length is clearly not going to impact our resolution as much as other column dimensions will. Something that makes more of an effect on speeding up your analysis and maintaining resolution is by using high-efficiency columns. Traditional columns range from 30 to 60 meters long, but Agilent's high-efficiency columns range from 20 meters down to 10 meters and have internal diameters of 0.18 millimeters. By decreasing the internal diameter from 0.25 or 0.32 millimeters to 0.18, we are not only going to speed up our analysis, but we also increase our separation powers. It's this decrease of diameter that allows us to decrease the length of the column, decrease the runtime, and maintain resolution of our peaks, creating a more efficient and productive GC. Here's how it works. Here we have a single molecule of TNT. As it travels through the column, it won't go in a straight line. It will interact with our solid phase or film layer on our column. Each time the molecule interacts with the solid phase, it will diffuse into the phase, come to an equilibrium, and then continue traveling down the column. The more phase interaction points, the more chances for our analytes to interact with the column and more potential for our compounds to resolve. This is also why when you increase the length of your column, you are increasing the number of chances for the analyte to interact and diffuse into and out of the column, and thereby will have better resolution. As you can see, as our TNT molecule travels through the column, it interacted with our solid phase 8 times. And while this sounds like a perfectly good number, but let's see what happens when we decrease our diameter of our column. Even when we maintain the same flow, our molecule of TNT will interact with our solid phase more times. By only decreasing the diameter, we have increased our potential interaction points from 8 to 15. This means we will have twice the amount of times where our compounds will interact and diffuse into and out of the solid phase of the column. And when there's more interaction between our compounds and our column, we increase our separation power. This is how smaller ID columns provide more resolution for the same length of column. And this is also why if we decrease the diameter and the length of the column, we can maintain resolution while still increasing the speed of our analysis and our laboratory throughput, meaning you can decrease your runtime while maintaining your resolution. This last example shows how we can shorten our runtimes using backflush. Backflush is a tool where you have controllable pressurized connection in the middle of your column, where you can switch the direction of the gas so that your compounds turn around the other way and end up going at your split vent instead of ending up in your mass spec. The top chromatogram shows that after the last peak of interest has eluted at 42 minutes, the column was heated up to 320 degrees Celsius for an additional 33 minutes to remove the high boilers. This caused the runtime to be approximately 75 minutes. Since our last peak of interest is at 42 minutes, this is where we will turn on backflush and turn up the backflush flow for 7 minutes. This will save us about 26 minutes of runtime, and the green trace shows a clean blank after the sample was backflushed, indicating that nothing was hanging out on your column and could potentially cause carryover or ghost peaks. And since we were able to stop our oven program at 280 degrees instead of having to take our column up to 320 degrees Celsius, we are also protecting our column's overall lifetime. Now, most people use backflush at the mid portion of the column, also known as mid-column backflush. It could also be used at the end of the analytical column, referred to as post-column backflush, where you have a smaller ID piece of fusilica transfer line going into the mass spec, and this can also allow you to swap columns without venting your mass spec. Either way you choose to use the purged ultimate union and backflush, it can save you time when you need it. In the previous slide, we showed an example of a longer, more old school method using backflush. And while saving over 30 minutes on a run is great, the overall cycle time is still going to be around 50 minutes, and we can do better than that. Let's talk about backflush done right, using all the tools in our chromatography toolbox. Both of these chromatograms are from a spinach extract, which is a very heavy matrix, so it is important to say that these samples went through the proper sample cleanup steps. Without sample prep, this whole analysis would be an uphill battle. The other thing about both of these runs is that the samples were run on a triple quad, so we were able to be very selective with our MRMs, or multi-reaction modes, and that helped us to speed up our method as well. Now on to the good stuff. In black, we have two 15-meter 0.25 columns, which equal 130-meter standard column. With mid-column backflush and proper sample prep, we were able to get this method down to less than 20 minutes. And if we translate this method using high-efficiency columns, which would be two 10-meter 0.18 columns with equal up to a 20-meter high-efficiency column, we were able to further decrease this method to less than 10 minutes. And when you can analyze 238 pesticides in less than 10 minutes, there is no excuse for sticking with a 60 or 70-minute GC method. And the high efficiency method is also compatible using hydrogen as a carrier gas, where we can even get our runtime down to 8 minutes. All three of these methods are compatible with our retention time locking libraries for pesticides, which not only make it easier for you to identify your peaks, but when you retention time lock your peaks, they stay in the same place no matter how many times you clip your column or how many different instruments you're running this analysis on. Regardless if you are using high-efficiency columns or backflush, one thing is certain. If you have any leaks in your flow path, not only will your column die faster, but you will be wasting gas. Using gas clean filters are a great way to know if you have a leak before it gets to your GC and helps protect your column from oxygen and moisture contaminants that may have crept into your gas line. On your gas filter, the blue indicator on top is the oxygen filter. Once this filter has reached 0.1 parts per million of oxygen, it will start to go from blue to dark gray. And when you see that, start seeing that nice blue filter turning dark gray, it would be a good indication that your filter is saturated and it's time to change it. The gas clean filter can be easily mounted on the back of your GC system, and the new 8890 GC even has an option for a smart sensor that, when connected with your GC, will alert you when it has become saturated. An increase in column bleed leading to column death won't be the only chromatographic symptom of oxygen in the column. Peak shape will also start to suffer as well. To demonstrate this, we will look at a common analyte used in test mixes, 2-ethylhexanoic acid, and how its symmetry is affected with the increase in temperature and oxygen. In this experiment, a wax column that was held at a final temperature for 12 hours and a controlled amount of oxygen was added to the carrier gas. You can see that the peak shape for this 2-ethylhexanoic acid at 250 degrees Celsius for 12 hours looks great. But as we increase the final temperature and add 10 parts per million of oxygen to the carrier gas, our symmetry starts to degrade. This is happening because the phase is getting damaged and causing peak tailing, at which point you may need to clip off a part of the front end of the column or replace the entire column, both of which cause downtime and loss of productivity. In addition to gas clean filters, a great way to avoid oxygen getting into your system is to use self-tightening nuts. Their spring-driven piston design adjusts to the natural expansion and contraction that will happen during multiple GC oven cycles. You don't need tools to use them, and there is one for the inlet as well as the one for the mass spec transfer line. And they use the same polyamide graphite ferrule. Overall, they are one of the easiest ways to prevent oxygen from getting into your GC flow path and increase your instrument's productivity. Using low purity gases can contain oxygen and other contaminants. And if you didn't already know how bad oxygen is for your column, we ran an experiment to show you just how bad. The chromatogram on top shows ultra-high purity helium carrier gas from injection 1 in black to injection 20 shown in blue. No change in retention time or sensitivity. Now, the bottom chromatogram, we doped our helium carrier gas with approximately 5% oxygen. Look at the difference between injection 1 and injection 20 in blue. You can see the dramatic decrease in response and retention time shift from the first peak. And look at the elevated baseline and background at the higher temperatures. That oxygen is inflicting permanent, irreversible damage on your column, which results in all of these chromatographic problems. It ultimately means that more money is spent on filaments, liners, and columns, and all but guarantees you'll be cleaning your source more often. The first cure for this potential problem is using ultra-high purity carrier gas. It's essential for GCMS. It should be 99.9995 or greater. My second tip is to use a high-quality GCMS gas filter. Agilent gas clean filters can be used with any mass specs. And one of the awesome things about these gas filters is that they're clear so you can see when the indicator starts to go bad. It's important to monitor these indicators closely and correct leaks present when they start to show up, or replace them when needed. We would recommend replacing them annually to avoid damage to your GCMS. And when you look at the indicators on the gas clean filter, another great feature is that the direction of change indicates whether your problem is upstream or downstream. Color change from the top down indicates a problem with your gas supply. Maybe your cylinder connection has a leak, or maybe you're not using high purity gas, or the vendor gave you a bad batch of helium. It happens. If the indicator changes from the bottom up, that indicates a leak between your filter and your GCMS. Correct the problem as soon as you can to keep your column and mass spec in good shape. If you happen to get a cylinder that's not 99.9995, also known as 5.9 helium, or we're in a situation where you could only get access to 4.9 grade helium, how much would a gas filter protect your column by filtering out oxygen? Here's an overlay of a background from a 4.9 grade helium without a filter on top and in black. You can see a very high background in the comparison to the 5.9 grade helium without a gas filter. But when we add the gas clean filter onto the 4.9 grade helium, the background drops lower than the 5.9 grade helium without a filter. There's a second filter or trap that should also be considered, especially if you aren't able to get ultra-high purity gases. The big universal trap should be installed vertically between your gas supply and your gas clean filter. This will help to increase the lifetime of your gas clean filter and add an extra bit of insurance in protecting your GC. One thing I like to do with both my big universal trap and my gas clean filter is to make sure I write down the date on it when I installed it. This is my extra reminder or my memory aid to let me know when I installed it. If all of a sudden I start going through gas clean filters quickly, there's a strong likelihood that my universal trap is saturated. And if I haven't replaced that universal trap in a while, it's a good idea to get a new one and replace that as well. Another tool we have to help keep your system leak-free is our combo leak detector and flow meter. The new leak detector is designed on the same handheld unit as the ADM flow meter, and one base can be used for both cartridges, leak detector and flow meter. The flow meter is able to detect nitrogen leaks as well, and while it's not as sensitive to nitrogen leaks as it is to hydrogen or helium due to the thermal conductivity differences relative to ambient air. The table on the bottom right gives you a few examples of the minimum detectable leak rates for a handful of gases. Where should we use the leak detector in our laboratory and around our instruments? First, let's start at the gas source with our leak detector, whether that's a cylinder or a tower connection. Next, follow our gas lines to the filter connection points and gas clean filter bases. If using gas clean filter system, be sure to leak check the swage fittings and the top and bottom of the ring holding the filter in place. Make sure you do this for all gas filters except if you have any for instrument air. Now let's flip around the GCMS and check out the back because we want to make sure we check all of our fittings on our GCMS except any ones again for instrument air. And do I have to check every single swage lock connection, even though I have 3 T's and a lot of connections to electronic pressure controls? Yes, you do. And if possible, don't use Snoop. Use a leak detector. Snoop can be really bad for EPCs in the flow path if it accidentally gets into the line. We checked everything leading into the GC. Now let's check the flow path. Be sure to leak check the septum nut and top turn weldment. Septum nuts will wear out and leak over time, and sometimes the top turns aren't tight enough. Open the oven door. You will need to check the inlet and detector connections. Even if you're using self-tightening nuts, it's a good habit to use a leak detector and check the connections has a good seal. Moving along the column, we get to the capillary flow technology or CFT connections, which also should be leak-free. No matter if it's a purged or unpurged CFT device, we don't want leaks coming in and destroying our columns and analysis. And last but not least, our mass spec transfer line. Again, even if it is a self-tightening nut, our nuts are being used, it's a good habit to leak check that fitting as well. Sticking with using helium as your carrier gas, there are 2 great options you can use either on their own or together to decrease your overall helium usage. Gas Saver is an option that is already available on your Agilent GC acquisition software. The whole point is to decrease the split flow after your compounds have made their way onto the column. While it is more beneficial for split mode injections, it can be used with splitless injections as well. We also have a helium conservation module that can be used with most Agilent GCs. This module has an APC where you connect your helium carrier gas, as well as a connection for nitrogen, and is designed to switch your carrier gas flow when your GC is in standby. Before we dig a little deeper into how each works, keep in mind that they can be used on their own or together to maximize your gas saving. Okay, so Gas Saver. Let's go over how it works and how to use it. The basic way to describe how it works is that it will decrease your split flow after your sample has vaporized and made its way onto the column. So why would we want to do this? The point of a split flow is to help dilute a concentrated sample so that the column and/or detector are not overloaded. Think of it like an inline sample dilution. We want to split that flow while the sample is getting vaporized in the inlet and making its way onto the column. But after that, we don't really need all of that gas flow going through our inlet. This is where we can decrease that split flow while keeping our column flow constant if we're in constant flow mode to reduce the overall amount of helium or any carrier gas really being used. If you are looking at the inlet portion of your GC acquisition software, there's a small box at the bottom left that says Gas Saver, and when you check it, it will enable this function. You will notice a flow and a time. The most important part is that you pick a time after you know that all of your sample has made its way onto the column. If you aren't sure, you can always set that time for a little longer initially and then decrease it once you are sure all of your compounds are present and accounted for. After that time, say 2 minutes or 3 minutes after injection, Gas Saver will automatically change your split flow to decrease the flow that you state in the box until your run ends. What about when you aren't running a sample and your GC is in standby mode? This is also a great time where you can use Gas Saver. Say you finished a sequence overnight. Do you really want the inlet to draw down 30, 50 to 100 mils per minute of flow or higher if using split ratios such as 100 to 1 for the entire night and waste that helium? No. Lower that flow to around 20 mils per minute, or make sure it does not go lower than 15 mils per minute because that's the lowest flow needed to purge the inlet, septum, and supply carrier gas flow to your column. But also make sure that your Gas Saver value is actually saving carrier gas. If your total flow is less than your Gas Saver flow, then you'd be wasting gas. The time to turn on Gas Saver is the time after injection. The system will then lower the flow to make sure you have enough flow to support column flow and septum purge. The recommendation is set between 2 to 5 minutes, but if you're using a mass spec, make it similar to your solvent delay. Make sure that all injection events are complete before the Gas Saver turns on. Gas Saver mode turns on post-injection and only turns off during the prep run and the injection duration. So you don't have to worry about setting up a post-run macro that would be loaded into a separate method. It's all in one. Now that we know how gas saver works, let's talk about the other option for conserving helium. Our helium conservation module can be used with our 7890, 8890, and 8860 GCs. This is a module where your carrier gas and nitrogen are both connected to an EPC, or electronic pneumatic controller, and is designed to automatically switch gas supply when the system is idle. You can set up a sleep and wake function, which is very helpful when your analysis is so routine that you know exactly when to expect your GCs idle, or in the case of a holiday when there's no lab work being done. This is a much better alternative than shutting off your GC, because when the wake function begins, you won't have to deal with waiting for heated zones to reach equilibration or potentially contaminations from ambient air exposure that could occur from shutting off your GCs completely. Here's how it works. When your GC is in normal operation mode, the flow is only coming from your carrier gas, helium. The helium pressure is set to 80 psi, as you normally would expect it to be, and the nitrogen is set to off, but any excess will go to purge. When the conservation module is active, like when the GC is in sleep mode, nitrogen pressure will be set to 70 psi, and the helium will be turned off. During this time, nitrogen will be flowing through your column. Something that is really important is that you need to connect your nitrogen line to a gas filter before it is connected to the helium conservation module. This is because impurities like oxygen and water can and will get into all gas lines. It doesn't just happen with helium. And if you aren't making sure that your nitrogen gas is clean, then you could be potentially adding impurities into your GC, which would make it that much longer to clear out of your system when you're ready to run. Gas clean filters aren't just for helium, folks. Once the system's switching from sleep back to run mode, it doesn't take much time for the GC to be ready to run. Here's an example of an analysis on a GC FID. On top, we see the original run with helium carrier gas before it's put into sleep mode. The two lower injections show the two injections after the GC is switched from sleep to wake mode. What we don't see is a difference in chromatography, which means you shouldn't have to worry about peaks shifting or funny things happening with your peak shape. So what about using the helium conservation module with the mass spec? Most people are always worried about adding nitrogen into the mass spec and would worry about the time it takes to purge the system after switching from nitrogen back to helium. We did an experiment where we compared the counts of nitrogen relative to our mass to charge ratio 69 peak in our PFTBA tune mix when setting the helium flow to 5 mils per minute and 2 mils per minute. You can see that while setting your helium flow higher will decrease your nitrogen saturation faster, within 15 minutes, both systems had a nitrogen background less than 1% and would pass mass spec tuning criteria. Some people may think that 15 minutes is a lot of time, but that's nothing compared to the time it takes to tune an LCMS. If for some reason you came into your lab early to run some priority samples and the GC was still in sleep mode and you had to manually wake it up, I would say to start the process, and in the time it takes to go get a cup of coffee or tea and check some emails, your system should be ready to go by the time you get back. Let's take a look at a tough analysis, ASTM D4815. We are going to combine the use of gas saver and the helium conservation module. This method normally uses a gas flow of 8 mils per minute and has a split flow of 70 mils per minute, which could be a lot of gas usage. When using gas saver only, one cylinder of helium would be expected to last about 71 days. So let's round down to say 2 months. That's pretty good and for just using gas saver. And this would end up costing around $1,537 per year. Now, if we add on using the helium conservation module, we are able to extend that one helium cylinder to last 376 days. So we went from 2 months per helium cylinder to 1 year. And because we are switching to nitrogen when the system is in standby, it will take about 340 days to go through that one cylinder of nitrogen, which is about 11 and a half months. And considering that the cylinder of nitrogen is much less expensive than helium, you only end up spending $356 in gas per year. That's a 75% decrease in gas cost. And this is one cylinder. Imagine if you were using a nitrogen generator. I know some people are worried about jumping to a gas generator right away because there can be an initial purchase cost. But if you start using the helium conservation module with the cylinder, you could probably save up for a nitrogen gas generator pretty quickly. And then you'd be able to decrease your overall gas costs by about 80% when you switch over to a gas generator. To continue our discussion on how to save gas and go fast, I'd like to discuss the age-old question of cylinder versus gas generator. Gas cylinders are easy to acquire and don't require maintenance from the user. When more gas is needed, one can call their supplier and have more delivered. The cylinder option allows for a lot of flexibility in the lab. However, there are some drawbacks to using gas cylinders. First, you will have to have your own pressure regulator. Second, there's a wide variety of gas options and purities. We've spoken about how Agilent requires 5.9 or 99.999% purity for carrier gas. Most gas suppliers are very good. However, sometimes a cylinder may come with a contamination, for example, argon, that if it's detected in the system can cause a very high baseline. Further, the user is subjected to availability of gas and reliant on the supplier. And as we've seen over the years, helium supply can go through cycles of being strained. All cylinder gases are required to at least have a gas clean filter for moisture and organic compounds. Gas generators are a nice option and allow the user to control the supply of gas. A benefit of the lab is that it's no longer reliant on the gas company. However, generators need regular maintenance. And for a hydrogen generator, using nanopure or high-quality deionized water is a must. The generator has a max delivery capacity, which means if you're wanting to expand your lab's capabilities by adding another GC, you may need to add another gas generator. Further, the upfront cost of a gas generator can be high. There's no helium gas generators as well. So similar to cylinders, the gas from the generator still needs to have a gas clean filter. And for hydrogen specifically, an additional moisture trap is recommended to guard against any extra moisture that may be created. So which is best? That depends on many factors and really depends on what's best for your lab and your instrument setup. As we think about gas supply, this is a good time to discuss the use of hydrogen as a carrier gas. Helium can sometimes be hard to acquire, which has led many labs to switching to hydrogen or seeing if it's a viable option. Hydrogen is readily available through cylinder or with the assistance of gas generators, and many labs are already using them with their FIDs. Hydrogen is sustainable and cheaply made from water. For those of us using atmospheric detectors, such as an FID, there aren't many drawbacks to using hydrogen as a carrier gas. Hydrogen is available on demand and has the flattest Van Deemter curve of all the carrier gases and will provide a faster analysis due to its faster linear velocity at the similar flow rates of helium. Also, this allows us to further decrease column dimensions such as length and diameter and speed up overall sample throughput. For those using a mass spec, hydrogen has the benefit of helping clean the source, but there are some things to consider. Let's go over some of our overall recommendations for using hydrogen as a carrier gas with GCMS. Here are our do's. Use a 9mm extraction lens and lower the column flow rate compared to the flow rate of helium. It's best to switch to a more efficient column as well. If you use a standard 30 by 0.25 column, the pressure at the control module for hydrogen will be about 1 psi, which is way too low. This is why it's better to switch to a smaller diameter column with the same number of theoretical plates, like a 20 meter by 0.18 of the same phase type. Always, always, always use gas filters. And if using a hydrogen generator, make sure the hydrogen generator is producing gas at least 80 to 100% efficiency. Finally, allow the system a longer time to bake out on initial setup. Hydrogen will help to clean out your system, but it needs an extra minute to get there. And some things to avoid are chlorinated solvents and hot inlets. A little bit of water, hydrogen, and dichloromethane can produce hydrochloric acid, and we really don't want to do that. Also, better to avoid heavily chlorinated compounds since they can dechlorinate like PCBs, and also avoid nitro compounds like nitrobenzene since they are likely to hydrogenate. So what analysis are the easiest to transfer over to hydrogen carrier gas? Hydrocarbon analysis and PAH analysis. Let's look at an example for why hydrogen carrier gas doesn't always work for everyone with GCMS. Using traditional ion sources, the fragmentation pattern can be a bit different due to spectral tilt when using hydrogen as a carrier gas. Here is the NIST mass spectrum for nitrobenzene that we would expect to see when using helium carrier gas. The molecular ion is 123 will be greater than the ion of 93 component of the mass spectrum. But when we use hydrogen carrier gas with a standard GCMS ion source, we see a flipped abundance of the 93 and 123 ions, indicating that nitrobenzene has been converted to aniline, and this is confirmed in the extracted ion chromatogram to the right. Spectral tilt, as I previously mentioned, isn't just seen in nitrobenzene. Several other compound classes show unacceptable spectral tilting when using hydrogen, such as pesticides, heavily chlorinated compounds, and flavor and fragrance compounds, while other compounds are more neutral or unaffected by spectral tilt, such as alkanes and PAHs. However, for those compounds that do show spectral tilting, Agilent has released the hydroinert ion source. The hydroinert ion source is similar to the traditional extractor source with the proprietary coating that reduces spectral tilt, a special candy coating, if you will. Hydroinert also is cleaned by hydrogen carrier gas stream, like we use in our jet cleaned cleaning source. That means that the cleaning time is virtually eliminated for the source because it's getting extra cleaning all the time. Now, when we look at the nitrobenzene again using the hydroinert ion source, we see that the hydrogenation that has been eliminated and the spectra is as expected. Here's another example using the pesticide Captan. On left, we see a greater abundance of the 151 mass to charge is created without the hydroinert ion source, and virtually no 149 mass to charge is seen. However, with the hydroinert ion source, we see that the abundance of the 149 and 151 charge ratios are maintained. Without the hydroinert ion source, dechlorination byproducts are being produced, which cause spectral tilt. So the hydroinert ion source retains the mass spectra, but doesn't maintain good calibration curves. Here we see an example of nitrobenzene calibrated from 0.1 to 100 micrograms per mil using helium and a traditional ion source on top, and hydrogen using hydroinert ion source on bottom. When we examine the average RF percent RSD, we see they are both excellent at 6.33 and 6.59% respectively. This shows that we can expect calibrations to be maintained when the hydroinert ion source is used with hydrogen as the carrier gas. Further, when using hydrogen as a carrier gas, the hydroinert ion source helps maintain sensitivity. Because the spectra is maintained, we are able to maximize the signal for our compounds of interest in scan, SIM, or MRM mode. Hence, when using the hydroinert ion source and hydrogen carrier gas, the spectra for many compound classes goes from unacceptable to differentiating. Even with the hydroinert ion source, there are considerations for method conversion to hydrogen. The conversion process will take some time and trial and error. Be patient and persistent, and the method will work out. But let's go over a few considerations. Think your plans through in advance and know what your musts are. What compounds must you analyze and be able to search using NIST? What column must you use? Are you able to use a method translator in advance to think about what changes need to be made to your oven program or column flow? Watch your inlet temperature and sample preparation. We still say to try and avoid using chlorinated solvents such as DCM when using hydrogen as a carrier gas. But if you must, please make sure to use an MMI inlet and start your inlet at a lower temperature because we don't want to be making any hydrochloric acid in our inlets. And remember that there are so many options out there than what we've shown today. It would take a lifetime to demonstrate every application using hydrogen and helium with every source configuration. So don't be afraid to think outside the box a bit. And most importantly, you still need to use gas filters even when using hydrogen as a carrier gas, both using a cylinder and a gas generator.